Variable stars are stars whose brightness, as seen from Earth, changes over time. Though this subject might seem dull or strike you as a textbook material, it actually gives a chance to dive deeper into astronomy because a simple light curve can tell us so much. We use it to find exoplanets and binary systems, measure distances, understand stellar evolution and complex quantum physics concepts, because stars are extreme physics laboratories. In fact, observations of distant Cepheid variables helped Edwin Hubble realize that galaxies are moving away from us, and that led to the discovery that the universe is expanding. So variable stars literally changed our understanding of the cosmos. You would stumble upon many different types of variables as they are classified with attention to detail, so there are a lot of groups and subgroups. But in this video, I will try to focus on the main ideas rather than waste too much time on the names. Variables are classified by a reason behind the change of their brightness, although you could also divide them by being regular or irregular depending on the lack or existence of a specific pattern in their light curve. Let's just start from dividing variables into two large groups: intrinsic variables and extrinsic variables. If the variability is caused by inner reasons like change of the physical properties of the star itself, this star is intrinsic variable. Pulsating variables are the best known example of such variables. These are the stars whose radius alternately expands or contracts as a part of their inner evolutionary process of aging. Pulsating stars swell and shrink affecting their brightness and spectrum. Pulsations can be radial if the entire star expands and shrinks as a whole, or non-radial if one part of the star expands while another one shrinks. This pulsation may or may not be regular. Astronomers are able to deduce this mechanism by measuring the spectrum and observing the Doppler effect. The Doppler effect causes sound coming from a car passing by you to change from high when it approaches you to low when it moves away from you. The same thing happens with light. Waves coming from an object moving towards us shift closer together so that the perspective frequency increases and light gets, well, bluer. Subsequently, if the object is moving away from us, we perceive its color, well, redder. So if emitted light spectrum changes periodically, it is probably a pulsation. Why does it happen? Stars pulsate because of an internal instability that causes their outer layers to expand and contract. This happens in a rhythmic way, like breathing in and out, and it's due to the energy getting trapped and released in certain layers inside the star. The most famous example is the Cepheid star, but there are many others, depending on the frequency and magnitude. It might take from several minutes up to several years for different stars to shrink and expand back. This is called a period. The light curve would have easily distinguishable peaks and troughs. We can see that shrinking usually happens at a slower rate than expanding back, because the brightness decreases slowly and then increases kind of like abruptly, right? Eruptive variables are another example of intrinsic variable. These stars experience eruptions on their surfaces like flares or mass ejections. They are usually irregular. In this case, luminosity variations are caused by material being lost from the star, or in some cases being accreted to it. Another possibility, brightness variations could be a sign of an approaching death. Another instance of intrinsic variables are cataclysmic or explosive variables that undergo a cataclysmic change in their properties, like nova or supernova, which are some of the most energetic events in the universe. A supernova can briefly emit as much energy as an entire galaxy. Can you imagine how much that is? The supernovas are caused by a white dwarf or a star core reaching a certain density limit, so that the balance between gravity forces pulling inwards and energy striving away from the star is off, and gravity wins, so that the inner layers of the star shrink and the outer layers are blown away at very high speeds, although the expelled matter can form a very beautiful nebula. Nova are also the result of dramatic explosions, but unlike supernova, they do not result in destruction of the progenitor star. Let's move to the second big group, the extrinsic variables. Luminosity variability can be caused by external factors as well. There are two main subgroups. First, eclipsing binaries. A binary star or a binary star system is a system of two stars that are gravitationally bound to each other and they are in orbit around each other. To the naked eye, binary stars might seem as a single object in the night sky. These stars can be distant or so close that they touch and exchange matter. When seen from certain angles, one star may eclipse the other, causing a reduction in brightness. Stars with planets may also show brightness variations if their planets pass between Earth and the star. You can see a sudden drop in brightness when the star is covered partially by its planets, or when one of the binary stars is hiding behind the other one. Rotational variables are stars with sizable sunspots, and they may show significant variation in brightness as they rotate, and brighter areas of the surface are brought into view. Bright spots also occur at the magnetic poles of magnetic stars. Stars with ellipsoidal shapes may also show changes in brightness as they present varying areas of their surfaces to the observer. The waves on the graph look pretty smooth, as you can notice, and that makes sense because the star is rotating constantly, and subsequently the brightness is changing constantly as well. Remember the Cepheid variables I've already mentioned? These are pulsating stars whose brightness varies periodically due to internal processes.
Cepheid variable stars exhibit a direct relationship between their intrinsic brightness or luminosity and the period of pulsation. The longer the period, the brighter the star.
This relationship is known as the Leavitt's law because Leavitt was the one to discover it, and it allows astronomers to determine a Cepheid's intrinsic brightness, like its true brightness, by measuring its pulsation period. This property makes them reliable standard candles for measuring distances to far-off galaxies. We can measure distance to a galaxy hosting a variable star through calculating the difference between apparent brightness, or how bright the star seems on Earth, and the intrinsic brightness, or a star's true brightness. Edwin Hubble's discovery of Cepheid variable stars in the Andromeda Galaxy offered the first solid proof that spiral nebulae were actually entire galaxies located outside of the Milky Way.
This breakthrough completely changed how we understand the scale and structure of the universe, because it turned out that the Milky Way was just one of the many countless separate galaxies.
And despite how obvious it might seem today, back at the time it was a big discussion. Some variables are neutron stars, and those are particularly interesting. For example, pulsars emit regular pulses of electromagnetic radiation, such as radio waves, X-rays, or gamma rays, thus the name. It happens due to their rapid rotation and strong magnetic fields. This emission is periodic with intervals ranging from milliseconds to seconds. Imagine how fast it spins, right? And those signals were first thought to be of alien nature, but as we can now see, they weren't. Variable stars, particularly compact types like pulsating white dwarfs or neutron stars, exhibit extreme conditions, intense magnetic fields, ultra-high densities, and elevated temperatures. These environments provide unique opportunities to test fundamental physics, because testing things that we seem to be sure about is an important part of work in science. Variable stars are an expressive example of how a simple graph could paint a whole image of new worlds we have yet to discover. I spent a lot of time analyzing variable star slide curves for a citizen science project on Zooniverse website, and I encourage you to test yourself and try classifying real light curves, at least for the fun of it, and of course for contributing to a real research project as well. I will leave a link down below. Thank you for watching. Check the resources and links I left in the description, and it would help me a lot if you would interact with this video, so like and subscribe please. Comment if you have any suggestions or questions. See you in the next one. Bye!